part 2, we're going to go over a binary classification problem in a good amount of detail. We will build out our model, pre-process our data, and go over the training. I also briefly mention a bit of the prediction procedure after training. And of course, we'll cover all those steps: building the model, pre-processing the data, training, any helper functions you need, etc.
Alright, so now for the next example. In this one we're going to quickly go over, not that quickly, but as quickly as can be done while being detailed and trying to give you some intuition. We're going to do an image classification binary problem, and I will show you, how I would tackle a problem, what I would do to tune hyperparameters, build out a model, some data pre-processing, and putting all that together. So for those of you who want to follow along, I am going to be using the same framework, which is Keras, same backend for that, which is TensorFlow, and the same IDE, which is PyCharm. For this one, we are using a Kaggle dataset, and it is called art images. You can see it here. Nothing too special about it, just some random one I picked. We will obviously not be using all these classes because there are 5. So what I did is went ahead and separated them, and I'm just working with sculpture and painting because those seemed pretty differentiable without too much trouble or stress. And per convention, I have split them. So what you'll see here is I have a data folder, and this will help us a lot as we're going along. So first things first, normally you want to split depending on the size of your data and depending on some other factors, but for the most part you want to go 80-20 with your data, 80 for training, 20 for validation, and depending on what you're doing, you can keep a little over for tests, but for the most part you'll probably be testing on a different set of data altogether, mainly the data you're trying to figure out or generalize to, right? So, and if you have, much more data than average, I would say, let's say you have 15,000 for each class, you can go with a higher training or a higher validation. At that point, you can even do 50-50. It really doesn't matter when you have tons of data, but the 80-20 split is to, give the model enough data to train on, but also not have too small of a validation sample that your validation accuracy and loss that you're seeing is, ends up being inaccurate because you don't have enough validation data that you're validating on. Okay, so I broke that down into train and validate. I did the 20%-ish, so I have 1,500 of each class in train and 400 of each in validate. And for this problem, as simple as it is, it should be plenty. But we will see when we get there, because I actually have to run through this. We're going in it blind. And just to show you, get info. I do in fact have 1,501. I don't think that's correct. Yeah, that's okay. Includes the directory. So just in case you didn't believe me. Any other things I want to add? Not really. We can go ahead and get into the code now. Alrighty, so unlike some tabular data problems, you're going to start, it really doesn't matter how you order this code, it's really your preference, but we'll start with the model and then I'll build the data joins, which we'll pull from our directories, as you saw in the previous example. Okay, sequential, and this is just, telling Keras API that we want a sequential model. We're going to build our first conv layer. We're going to put 32 units in that, and we will have a filter size, kernel size 3x3, and then our input shape will be 3 by 150 by 150. And it doesn't matter if all your photos are not the same size beforehand. They will be resized, but of course you want to have pretty similar aspect ratios, so huge portions of the photograph aren't getting, or the image photograph aren't getting cut off. Okay, and then we're just adding our activation to that layer, and we'll run with Arelu. And then finally, we are going to add our max pooling layers. And if you don't remember, max pooling layers are going to take the max over cells of our image data matrix. And this is done for a couple of reasons, as I mentioned previously. The most important of which is reducing the complexity and the number of features that the model is learning. So we want to increase the effectiveness of the features and the relevance of the features that we're learning, while not just learning a bunch of ineffective and irrelevant features. Okay, and then we'll just go ahead and add that same exact layer again. We're going to have two conv layers with 32 units, or 32 filters, sorry. You can call them units too, it's not technically incorrect. And then we're going to do the same thing, but in these bottom two, we're going to add 64. And normally adding some variance in your unit size, for the most part, when you're doing tabular data in the hidden layers, you will have the first hidden layer will have the most units. In convolutional neural networks, conventionally, you will start with the smaller unit layers, followed by the ones with more. But you can get pretty decent results the other way around. I won't go into the theory behind why that is, because it can get a bit complex situationally, but go ahead and look into that, especially when you're working on a problem. Okay, and now we have added those two, and next we need our flatten. And if you will remember, our flatten converts our 3D image feature matrix into a 1D feature vector, which is what we need for our dense layers to be able to really do anything with them. Alright, so now we're going to add our dense layers, and for this example I'm just using 2, and that'll of course be problem dependent, depending on the complexity of the problem that you're working on. And then we're going to add a ReLU activation to that as well. On top of that, we'll add dropout to reduce overfitting. And we will just copy that dense layer. And then our last part of the model will be the output layer. And that's going to have 1 unit and a sigmoid activation because we are doing binary classification. And then again, because this is a binary classification problem, we're going to use binary cross entropy for our loss function. optimizer. We'll use RMS prop. You could use a few different types of optimizers. In general, the main two optimization functions you'll end up using are stochastic gradient descent and atom or NADM, which is the Nesterov momentum version of atom. It tends to converge to the global optimum more often and in less steps than regular atom. Okay, and then our metrics are going to be, of course, accuracy. You could also use loss, but that's a little bit harder to interpret in general. Okay, so now that we've built our model, we're going to go ahead and define our batch size and our image data generators, as we saw in the example before. So our batch size will just work with 16, and then our trained data gen, which again is going to be our image data generator. So if you remember from just a little bit ago, this will define how you transform and pre-process your data in order to, both prevent the model from seeing the same image more than once, and also allow the model to learn target class from a variety of perspectives. Okay. Rescale. Our shear range, we'll go with 0.3 on this one. We'll go with a zoom range of 0.2. And if you remember, the shear range is almost going to be a affine rotation across the central axis. That's not the precise definition, of course, but that's the higher level, essentially output of a shear range transformation. And then we'll do a horizontal flip as well. And then that should be good for this problem at least. Our target classes are fairly different and pretty easy, so I don't think we should have too much trouble. And then we have to create our test data gen, and all we're going to do with this, because of course it's our test data, we're just going to rescale it, so we're not going to perform any transformations on that. Okay, and then we have to turn those data gens into actual generators. And we're going to use the flow from directory function. It's pretty much the same as the flow function that we looked at earlier, but we're just flowing from a directory instead. Before we defined the photos beforehand that we're going to perform transformations on, and here we are just flowing from the dir. So all the images in whatever directory will get transformed. And we're going to use the entire train, and it will deal with the classes and all that on its own, which is really nice. That's one of the nice things about the high-level Keras API. And what we're doing here is we're setting our target size. And the reason we're doing this is because, one, we want all our photos to be the same size, of course, and also we want a square image. You can, in theory, use different perspectives, but well, sorry, not different perspectives, different aspect ratios. So you could use like something like a 4:3 or 16:9, but your results aren't going to be as good. It will mess with your transformations, things of that nature. So whenever you can work with square photos, you can, rescale them and format them into a square perspective or aspect ratio via Python or some online tool. But in general, we want to stick with square images. And our batch size is going to be our batch size, of course. Our class mode. What is it? Oh, did I not? Yep. Okay. So our class mode is, of course, going to be binary because we are working in the binary context. And then that is good to go. Okay. And then we're going to create our validation generator. And this is, of course, going to be for test or validation. Okay. Data/validate. We will also have a target size, of course, of 150 by 150 for the same reasons. Our batch size, of course, will be the exact same. And then our class mode will just be the exact same. So not too much different there, right? Okay, and then we're going to tell our model to fit those generators. And our first one will be, of course, the train generator. So our steps per epoch, this is going to be our total number of photos divided by our batch size. So in this case, it'll be 3,000 divided by batch size. Our epochs, which is the amount of times we will go through the entire training data set that we have for ourselves. We'll just set that at a default of 50. Depending on how training goes, you may want to increase that, lower it, add something like early stopping. So if your training stalls for so many epochs, you can just tell it to stop, or starts to diverge as well. We're going to set our validation data, and that is going to be our validation generator. Our validation steps is going to be 800 because we have 400 and 400 divided by the batch size. Okay, I think that is it for that. And then the last thing is we just have to save our weights at the end. Let's call it model weights h5. And now we can go ahead and start training. This is pretty conventional for what you will experience when you're doing an image classification problem, or in general most computer vision problems. Of course, if you're doing something like object detection, there will be a few other details like incorporating the bounding box, and the training is a bit different as well because you have to have bounding boxes on your training data. So it can get not more difficult, but a bit more arduous as far as prepping your data and things of that nature. But in general, most of the steps are going to be fairly similar to this. Okay, now we can go ahead and run that and see how we do. Okay, so to clean that up, I just created this little script using a couple different things. Pill, NOS, and glob. Glob is a package mainly used for this purpose. What glob.glob will do is take the entire directory and make a list of the relative paths. and it can also do full paths, of course. And then in order to check if the photo is broken, we're first opening it. That will catch most of the broken photos, and then all of the others will be caught by im.verify, which is going to try and verify whether or not the image is corrupt or if there's anything wrong with the image yet. And if there is, so if there is an IO error, we're just going to remove the photo. And that worked like a charm. Okay, so fingers crossed, this will work now. Okay, we actually have to change that steps per epoch now. It's now 29:39, I believe. Let me just double check the amount in here. Yep. Okay. So fingers crossed this should work now. And let's take a look. So our accuracy is, as you can see, is increasing quite quickly. It seems we'll probably, depending on whether the validation accuracy is similar. Okay, we're gonna have to do that with the validation data as well. Jeez Louise. Anything? Okay. What? Oh yeah, it's validate. Alright, let's take a look see at this now. How many did we remove? 3, 4, so that one will be 784. Okay. Now we should be good to go. See, it's a good thing I showed you this live and didn't, test it all beforehand. I wanted to go in cold because, any issues that I run across while I'm building it, you will then know about and know the steps I use to go ahead and solve them. And that's an important thing to both understand and have an intuition for, because if not, you'll spend a lot of the time just trying to bat away various errors, some of which you may not even know the root cause of. Okay, so should be good now. Let's go ahead and see what the validation accuracy turns out to be. I would assume it won't overfit within the first epoch. That can happen sometimes if it's a complex problem and validation doesn't. And ooh, wow! And even the sculpture has some broken ones. Just a bunch of broken images in that data set, eh? Okay, let's see what changed. Okay. So that's 391, 784 minus 9 is 775, not 3. Okay. Okay. Now, I don't think we should have any more issues. Let's go ahead and jump into this. There's really not any more issues we could potentially have. So I'm keeping my fingers crossed, and I'm knocking on some wood at the same time. Okay, and yeah, that did in fact work. That's great. Okay, yeah, and see, since the problem is so simple, and because the classes are so different, within one epoch, we're already reaching 93% validation accuracy, which is, fantastic. We could go ahead and call it a day, depending on, what's required of us, what your potential client, or what the research project calls for, or what you want. Different projects will have different requirements. Some will have accuracy requirements. Some will have, speed requirements. Some will have complexity requirements, etc. Right? And as you can see, we're already Oh, it dropped already. So as you can see, after one epic, we were pretty much done, and we could incorporate something like a couple more dense layers with more aggressive dropout to reduce the overfitting, because it's already overfitting after just a couple epics. Well, not too bad yet, but yeah, and we would definitely want to incorporate something like early stopping for this. But yeah, so that was pretty painless, except for those silly errors. But I'm glad those popped up, because it's important to know how to figure those out, and the first things to check and all that. Okay, so that will do it for this example. If you want, you can go ahead and, if you were following along, play around with it some more, try and squeeze out a bit more accuracy. That will definitely help improve your skills, and more importantly, your intuition.